Welcome to AI Paper Slop, where we summarize AI and tech papers for technical folks who want to stay up to date. Today's paper is Parallax, Parameterized Local Linear Attention for Language Modeling, from researchers at Northwestern, Tilda Research, and UW. So getting straight to the core insights here, standard Softmax Attention is bottlenecked, and efficient alternatives, like Mamba or linear attention, they sacrifice in-context associative memory. This paper introduces Parallax, which is a scalable, parameterized form of local linear attention, or LLA. It basically adds a parallel covariance correction branch to standard Softmax, increasing arithmetic intensity so it actually runs faster than FlashAttention 2 and 3 on Hopper GPUs. Plus, it shows massive perplexity improvements at the 0.6 billion and 1.7 billion pre-training scales. But there is a massive twist. This architecture only works if you train it with the Muon optimizer. Adam W. completely breaks it.
Yeah, it is a wild finding.
Okay, let's unpack this. We have this new attention mechanism that's supposedly mathematically superior, and it's heavily hardware optimized. But to really get why Parallax even needs to exist, we have to look at the fundamental math flaws of the current attention mechanisms that you and I use every single day.
Right, because, well, if we view attention through the lens of a test-time regression framework, standard Softmax attention mathematically acts as a local constant estimator.
Okay.
For the rigorously mathematically inclined folks, it's specifically the Nadaraya-Watson estimator. But, for those who haven't brushed up on kernel regression recently, think of it this way. It essentially treats the key value pairs in your context window as training data.
Right.
When a new query comes in, it predicts the value for that query by just taking a locally weighted average of the surrounding data.
So I like to think of Softmax as basically just looking around and averaging the nearby data points. It is a very safe estimation technique, but it's fundamentally limited because it just flattens nuance.
Exactly. It's safe, but flat. And then on the flip side of the ecosystem, we have linear attention and state space models, like Mamba.
Whoa.
They give you that beautiful subquadratic efficiency, which allows for basically infinite context windows. But they inherently struggle with in-context information retrieval.
Right, that associative memory.
Yeah, that ability to pinpoint a specific needle in a massive haystack. It drops off significantly compared to Softmax.
Which is exactly what brings us to the theoretical fix, right?
Ah.
Local linear attention, or LLA. By upgrading that local constant estimate from Softmax to a local linear estimate, you get a provably superior bias variance trade-off.
You do. You are no longer just lazily averaging your nearby points. You are actually fitting a localized linear function to the actual geometry of the keys around the query.
It's like instead of just taking the average temperature of a room over an hour, you're actually drawing a localized trend line through the specific temperature fluctuations right around the exact minute you care about.
Yes.
It's obviously far more accurate. But, there has to be a catch, right? If it's this much better, everyone from OpenAI to Meta would just be using exact LLA right now.
The catch is computational exhaustion.
Of course.
Yeah, to do exact LLA, you can't just run a simple matrix multiplication. It requires running a parallel conjugate gradient solver, a CG solver, for every single token to find that optimal projection.
Wow. Every token.
Yeah, and for those who haven't had the pleasure of writing one recently, think of a CG solver as an iterative algorithm. It's trying to navigate this massive grid of linear equations by constantly ping-ponging data back and forth to find the optimal path.
That sounds incredibly expensive.
It is totally ruinous to your memory bandwidth. If you look at the memory access pattern, it requires T times L times D memory access. T is your iteration number. L is sequence length, and D is the dimension.
Right, okay.
So if you have to run 10 iterations, you are scanning the memory 10 times per token. It completely destroys your memory I/O budget. And on top of that, LLA's exact CG solver is incredibly sensitive to low precision formats. So it is aggressively hostile to modern hardware paradigms, like FP8 or BF16, that rely on reduced precision.
Wait, hold on. Let me make sure I'm wrapping my head around this. Exact LLA is mathematically beautiful, but it requires an iterative solver that forces you to read from memory over and over again for every single token.
Right.
And it hates the low-precision formats that actually make modern GPUs fast. So it's basically computationally impossible for large language models.
Pretty much, yeah.
And that is exactly where Parallax comes in, right?
Yeah.
The researchers needed to parameterize the map to bypass the solver. So how did they actually eliminate that exact per-token CG nightmare?
Well, they completely dropped the numerical solver. They just swapped it out for a learnable projection matrix, which they denote as W sub R.
Okay, a learned matrix.
Yeah, instead of iteratively solving for the best path, Parallax takes the layer input, x, and passes it through this new learned matrix to create a probe vector. They call that probe rho. So a rho simply equals w sub r times x.
So instead of just projecting the classic Q, K, and V matrices that we're all used to, the model now operates with Q, K, V, and this new R matrix.
Exactly. And with that substitution, the parallax output equation becomes beautifully simple to calculate. It's literally just the standard softmax output minus the key value covariance multiplied by that new probe, rho.
Oh.
Yeah, you are taking the safe softmax baseline and correcting it with this covariance branch. However, to make this structurally stable, the authors specifically had to set a term called the boundary amplification factor, or eta sub I, to absolute 0.
Wait, so if we aren't solving the math exactly and we drop the boundary factor, are we just guessing the correction? I mean, my understanding is that in exact LLA, the boundary factor is there for a reason. It compensates for queries that sit right at the extreme edge of the key distribution. So it sounds like we're just hacking the math until it compiles.
What's fascinating here is that this specific choice, dropping the boundary factor and using a learned probe, actually places Parallax squarely within a wider family of test-time regression learners. It isn't a hack at all.
Oh, really?
Yeah. When you analyze Parallax under what's called the wide bandwidth limit, meaning you look at the math as the softmax kernel becomes uniform, it is deeply theoretically connected to architectures like a fine linear attention and a fine mesonet.
Okay.
It proves that what we traditionally call the query is actually just a directional readout probe. You aren't guessing. You are giving the model a parametric pathway to learn the optimal directional probe directly from the training data.
Gotcha.
If you left the boundary factor in with a learned probe, it would aggressively overcompensate and basically blow up your training dynamics.
That actually makes a lot of sense. You're replacing an unstable, rigid mathematical rule with a learned, data-driven pathway. But, you know, a new elegant equation is completely useless if it runs slowly in the real world.
Definitely.
So let's decode the hardware magic here, because mapping this theory to modern GPUs is where this paper really blew my mind.
It is a genuine masterclass in hardware-aware design. Parallax uses a streaming algorithm very similar to FlashAttention to handle the memory efficiently, but it adds that parallel covariance branch we just talked about.
Right.
Crucially, both the softmax branch and the covariance branch share the exact same key value, or KV stream. They aren't loading the data twice.
And because they share that stream, it fundamentally changes the arithmetic intensity.
Yeah.
Let's define that real quick. Arithmetic intensity is the ratio of floating point operations, the actual math, to high bandwidth memory traffic, which is just moving data from the memory chips to the cores.
Precisely. Parallax basically doubles the arithmetic intensity. And to understand why this is a massive win, you have to look at how decoding works on NVIDIA Hopper GPUs like the H100 or H200.
And current workhorses.
Yeah. During the decoding phase, you are processing queries token by token. Because you're operating on tiny single query rows instead of massive matrices, your math operations are trivial, but your memory loading is massive.
Oh, okay.
So this leaves the actual tensor core accumulators, the parts of the GPU that do the heavy lifting, just sitting idle.
It's like a master chef who can chop vegetables at lightning speed, but has to wait 10 minutes for the sous chef to run to the fridge and bring back the next onion.
That's a great way to put it.
The chef is the tensor core, the sous chef is the memory bandwidth, and the chef is just standing there with a knife doing nothing most of the time.
That is the perfect analogy. Parallax is essentially giving that chef a side task, like whisking a complex sauce to do while waiting for the onion. Parallax takes its extra R and K matrix multiplications, these heavy WGMMA instructions, and just sneaks them right into those idle cycles.
Wow.
The GPU is waiting for the memory anyway, so you might as well force it to compute the covariance branch.
So we are literally doing more math, but doing it faster because we're just filling up empty hardware cycles that were previously wasted.
That is exactly what is happening. By shifting the attention mechanism from a memory-bound regime waiting for the sous chef to a compute-bound regime, they have hit the holy grail of current AI hardware optimization.
That's incredible.
The results speak for themselves. The authors wrote a prototype decode kernel in Qt.SL, which is a library for writing ultra-optimized CUDI kernels directly at the hardware register level. This Parallax kernel outperforms both FlashAttention 2 and 3.
Amazing.
Yeah. In a compute-matched setting where they halved the head dimension to make the FLOPs identical to standard attention, they achieved a 1.54x speedup. Even in a strict IO-matched setting where memory access is identical, they still saw a 1.14x speedup.
Okay, so they've solved the hardware bottleneck, meaning we can finally train this at scale. But that raises the ultimate question, right? When we actually let this loose on a billion parameters, does this theoretical trendline math actually make the model smarter or just faster?
Right, let's look at the data.
Yeah, looking at the pre-training data, starting with the synthetic tests on the MAD benchmark, Parallax just dominates Mamba, Mesonet, and gated DeltaNet on in-context recall tasks.
And importantly, that synthetic success isn't just a parlor trick. It translates directly to real-world LLM pre-training. The authors trained a Qwen 3 architecture at the 0.6 billion and 1.7 billion parameter scales using the ultrafine web dataset.
Okay, solid dataset.
Across the board, Parallax showed consistent, significant perplexity improvements over standard softmax transformers. And, those lower perplexities translated to better downstream accuracy on major benchmarks like HelloSwag, PIQA, and ARC.
Now, I want to highlight the rigorous controls they used here because it's so easy in AI research to just add parameters and claim you built a better model.
Oh, absolutely.
They tested against a parameter-matched transformer where they literally just added query heads to the baseline softmax model to perfectly match the parameter count of Parallax's new R matrix.
Right.
They also tested a compute-matched parallax, where they penalized Parallax by having its head dimension, but boosted its feed-forward network dimension to keep the math operations equal. The performance gains persisted in both of those highly constrained scenarios.
They're very robust.
So what does this all mean? It means this isn't just a trick of parameter counting or throwing more compute at the wall. The Parallax architecture itself is fundamentally structurally more capable of learning and retaining associations.
It is a genuine Pareto improvement, faster and smarter. But this brings us to the most surprising finding in the entire paper. The pre-training results are incredible, but the authors discovered that those results completely vanish if you use the wrong optimizer to train it.
Here's where it gets really interesting. Think about your standard training loop. You build your model, you blindly type optimizer equals Atom W, and you hit run. As ML engineers, we treat optimizers and architectures as completely modular Lego bricks.
Yeah, everyone does it.
But Parallax exhibits a massive, fatal optimizer architecture interaction. It absolutely requires the Muon optimizer to work. When they trained Parallax with Atom W, and they tried both cosine and WSD learning rate schedules, its performance degraded right back down to standard transformer levels. The architecture essentially broke.
It's a paradigm shift that should make every researcher sit up and take notice. To understand why Atom W breaks it, we have to look at a metric the authors track called the correction-to-output ratio, or COR.
Okay, COR.
This measures how much the new covariance branch actually affects the final output compared to the standard softmax base. When you train with the Muon optimizer, the COR reaches over 8 in the deep layers of the network.
Oh, okay.
That means the covariance correction branch is doing massive heavy lifting. It's driving the model. With Atom W, the COR stays incredibly low. The covariance branch essentially flatlines and shuts down.
So the model just ignores the new math. The authors trace this back to something they call magnitude tension. Basically, Atom W actively causes spectral collapse in the W sub R projection matrix. The stable rank of that matrix just plummets, rendering the probe vector totally useless.
Yeah, it completely neutralizes it.
But why? Why does Atom W, the king of optimizers, ruin this specific matrix?
It comes down to how Atom W normalizes its updates. Atom W normalizes based on a rolling variance similar to RMS prop. This variance normalization intrinsically flattens the dimensional importance of the weights.
Right.
But the W sub R matrix needs to be highly directional. It is literally acting as a geometric probe to read the covariance structure of the keys and values. When adder W flattens the geometry, it turns that sharp directional probe into uniform mush.
Gotcha.
That is spectral collapse. Atom W intrinsically fails to maintain the necessary geometric structure.
And Muon doesn't do this.
Exactly. Muon, on the other hand, uses Newton-Schultz iterations to approximate polar factors for its updates.
What does that mean physically?
Physically, it ensures the update condition number is exactly 1. By keeping the condition number at 1, Muon updates the matrix via orthogonal transformations. It rotates the weights without stretching or squashing the space unevenly.
Oh, nice.
Yeah. By maintaining that orthogonal geometry, Muon preserves a very high stable rank for the W sub R matrix. This yields what they call a high covariance probe alignment, or CPA. The probe actually stays sharp and aligns perfectly with the leading directions of the KV covariance.
The experimental proof they offer for this is just wild. They ran a gating experiment where they put a learnable sigmoid gate on the parallax correction branch, essentially giving the model the choice to use it or ignore it.
Right.
Under Muon, the model actively learns to open the gate and heavily route data through the new architecture. Under AtomW, the model actively learns to close the gate. It literally unlearns the architecture because the spectral collapse makes the branch output garbage, so the model shuts it off to protect the baseline softmax loss.
If we connect this to the bigger picture, it raises an incredibly provocative, almost terrifying question for the entire field of deep learning. How many failed attention variants or novel linear architectures in the literature of the last 5 years were actually amazing, but just suffered from spectral collapse because every single researcher tests their new model with AtomW by default?
That is a staggering thought.
We might have discarded entirely viable, revolutionary architectural paradigms simply because of an invisible optimizer mismatch.
All those abandoned GitHub repos might actually hold the key to next-generation models. They just needed Muon.
Exactly.
Before we wrap up this deep dive into the architecture, let's look at one last piece of the technical analysis: how this Muon-optimized parallax model actually distributes its attention differently across a prompt. We know standard softmax suffers heavily from attention sinks.
Yeah, the sync problem.
For those unaware, this is where the model dumps excessive, almost panic-driven probability mass on the very first token, like a period or a start token, just to safely route unneeded attention away from the real text when it doesn't know what to focus on.
Yes, it's a known flaw of standard attention. But Parallax significantly reduces that sync ratio. Furthermore, when you measure the attention entropy, Parallax produces base softmax weights that are much more diffuse and much higher entropy than a standard transformer.
Oh, interesting.
The softmax is spreading its attention out much more evenly over the context.
So does this mean the model is essentially delegating tasks between its two branches?
Exactly. It's a beautiful division of labor. The model uses the standard softmax branch for broad, diffuse, contextual aggregation. It's essentially gathering the general vibe and wide context of the prompt.
Right.
It then offloads the fine-grained, sharp token discrimination and exact associative retrieval to the new covariance branch. This division of labor is precisely what makes the parallax model inherently more expressive without requiring deeper layers or wider embedding dimensions.
To quickly recap this deep dive, Parallax takes the theoretical promise of local linear attention and makes it highly practical for modern LLMs. It upgrades the core math by introducing a learned probe instead of an expensive numerical solver.
Yeah.
It actually runs faster than FlashAttention by sneaking dense covariance math into idle GPU cycles, effectively turning a memory-bound bottleneck into a compute-bound advantage.
Exactly.
And perhaps most importantly, it proves that architecture and optimizer are inextricably linked, specifically requiring the orthogonal updates of the Muon optimizer to avoid the fatal spectral collapse caused by AtomW. If you are building models or researching new architectures, you should definitely check out the Parallax code repo linked in the paper to test those Q2DSL kernels and the Muon implementation for yourself.
It truly is a masterclass in full-stack AI research. They solve problems from the theoretical non-parametric statistics all the way down to the hardware registers of the H200.
And we want to leave you with a highly specific thought to mull over. The paper notes that linear attention, DeltaNet, and MesoNet all deliberately drop the intercept in their mathematical formulation because it traditionally causes instability. But if Parallax just showed us that reintroducing the intercept and combining it with the Muon optimizer unlocks massive scalable performance, what happens if you take those older models and apply Muon to an affine DeltaNet? Could we unlock a whole new generation of linear models that the industry previously thought were dead ends?